Why do liquids unmix at low temperatures? Who knows? So, we're going to talk about liquids mixing and unmixing, and try, by the end of the second video, probably, should have an answer for why liquids tend to mix better. Most liquids anyway tend to mix better when they're hot, and why they don't mix so well when they're cold, which you probably noticed if you've ever tried to mix, to wash up oily pans or something like that. It doesn't work very well with cold water. So, we've talked about this important parameter in thermodynamics already, called the Helmholtz free energy, which is given by the sum of something called the internal energy, and which we've seen before, and our temperature times our entropy term. So for this video we're just going to talk about this second term and compare what it's like when they're mixed and when they're unmixed. The end goal is to have a free energy term for mixed and a free energy term for unmixed, because if we have that, then if this one's bigger than this one, then we can say thermodynamically the liquids will tend to mix together, and if this one's bigger than this one, then we can say they'll tend to separate. So for this video we're just going to concentrate on this part. I'm going to talk about A and B molecules, and that's just two different kinds of molecules. So it could be oil and water, it could be benzene and something else, I don't know. Any two liquids you care to mention. I have just made them all A's, which is bad. So A and B molecules. So they could either be separate or sort of all mixed together. Like that. Something like that. So, we're talking about entropy. So let's first talk, so let's define our entropy. We're going to use the Gibbs entropy, because I think that one makes more sense. And so that's our K Boltzmann times the sum of over possible microstates times probability of each microstate occurring, being the one that's occurring, and the log of that probability. Just put a line there. So obviously if there's only one possible microstate, then you're going to have a 1 there, and log of 1 is 0, so you would have 0 entropy. And actually that's exactly what we get in the case where they're unmixed. Because we've got A molecules and B molecules, and we say every B is the same as every other B, then if we swap two B molecules over, let's talk about marbles in a jar or something like that. So we got some blue marbles and some red marbles. If we swap two blue marbles over, it looks exactly the same. Doesn't change anything. So when they're separate, when we got blues here and reds here, and we know that's the case, blues are here, reds are here, they're not mixed in any way, then that's only one possible microstate. We actually have no missing information. We know everything there is to know about the system. So our entropy for the unmixed case is 0. So the unmixed case is really easy. So what's it when it's mixed? Well, we can imagine something like in our jar of marbles, we imagine like a lattice. And in each lattice bit, there's either a blue marble or there's a red marble. One or the other for this problem. Although you could generalize it to having different green marbles and all that quite easily. So we got a little square and blue marble and red marble. What's the probability of it being either? Because each square, because each square in our jar is equivalent, we can consider what's the entropy of just one square and then just add it up for every single square. We multiply by the number of squares to get a total entropy. But actually, to make things simpler, it's nicer to not have total entropies and to have entropy per square, per cube, per lattice bit, per lattice point. That's simpler because it generalizes to whatever volume of liquids we want to talk about. We want to talk about a 10 liter mixture, works just as well as a 10,000 liter mixture. So let's consider what's the entropy for just one little lattice cube that could either have a blue marble or a red marble. Well, we sum over probabilities. What's the probability of it being a blue marble? Well, it's quite easy. We just take the number of blue marbles and divide it by number of marbles. And we define this, or a similar quantity to this, as something called the volume fraction. So, define it down here. We have volume fraction, and we would just say, we actually define it as the volume of, let's say volume fraction of liquid A would be volume of A divided by total volume. Well, that, you can't really see that. There we go. So we have this, and that's essentially our probability. We have 10,000 marbles, and 1,000 of them are red marbles. Then the probability of a single one of our squares having a red marble in it is just going to be 1 in 10. So this makes our S mix quite simple. It just becomes minus K Boltzmann times, and there's going to be a sum, so this may not look very neat, but we'll try. Volume fraction for A times log of that plus volume fraction for B times log of that. Ta-da! But it gets simpler because we know there's only two kinds of molecules. Then in this special case there could be more in other cases, but in this special case there's only blue and red, so we know that this number is going to be 1 minus that number, because they've got to add up to 1. So we just replace that. And you can test this out by differentiation, finding the maximum, or you can just trust me that the maximum is going to be when phi is 0.5, which kind of makes sense. If you have equal numbers of blue and red marbles in your jar, then if you pick a random marble, you got a 50-50 chance. If you've got much less blue marbles than red, then when you pick a marble, it's less of a risk. You have less missing information. You know more about the jar, or what you're going to get when you pick that random marble, if the probabilities are uneven. A nice way of working out entropy is what you would do if you were asked to bet on it. Actually works quite well. But in any case, we've worked out S unmixed, which was the easy case, and S when it's mixed, and we can now find the difference, which is just going to be the same as this, and that leaves us in a good place for the next video,